This is some of the hardware that we used, or pretty much all the hardware that we use, excluding the PC. On the left side, you can see the microphone, you see the D2 board, and the breadboard, which we use to set up the circuits for both the servo motor and the DC motor, which you can see both of them right there on the bottom right side. And there's a system diagram. We have the microphone going into the board, the big block in the middle represents the board. It has all the components, the SRAM, SDRAM, the parallel ports. We use the parallel ports, of course, for the output pins. We only use the JP0, only two other pins using to control, one for the servo motor and one for the DC motor. They're on the right side, you can see there. And turning the board, we use three switches for each word. Switches 0 through 2 are used for recording go, and switches 3 to 5 are used for stop, and switches 6 to 8 are used for open, and switches 9 through 11 are used for close. Then depending on which switch is high, the result of each computation should be saved on the different addresses to give us access to them whenever we need them for the recognizing mode. And the push buttons. So key 1 is used for recording in training mode, and key 2 is used for the playback function, which we used in case we didn't have like a good setup in the training. We could check it, and if it's good, then we'll keep it. Otherwise, we'll record it again. And recognizing mode is activated when both switch 0 and switch 1 are high. Then, depending on which switches are high, the corresponding LEDs will turn on whenever the push button is pushed. So you can switch the switch anytime and it won't do anything. The LEDs won't turn on until you push the key 1 push button. And some of the LCD messages are switch error, which comes up whenever more than one switch is high, except when in recognizing mode, of course. And no word spoken is when there's no word detected on the microphone, and word detected is when it detects a word. The message rec go word shows up when you're recording for the go word, and rec stop word for stop word, and so on, open and close. And then the last messages are for the recognizing mode. So if there's no match, it'll display no match. If detected go, then detects go, and detect stop, detected open, and detected close. And the expansion header pins, we are using, like I said, the two pins for the DC motor and the servo motor, and then we use the ground pin and the 5-volt pin to drive the motors. So if you set it for output, the pin will give us a 1.3 volts, which will drive the N-channel MOSFET, and which will turn on the voltage going into the motor. And so the fan turns on when go is detected, and the next time the stop is detected, the fan should turn off. So this is just a little circuit of the DC motor. So low side N-channel MOSFET we're using to switch it on, and we're using the pin furthest to the right on the top of the JP0 port.
We needed an easy way to generate the PWM signal for our servo motor. So we used the following 555 timer circuit, and in this circuit we used an N-channel FET to bypass the R2 resistor, and in doing so this would give us a maximum pulse width of about 2 milliseconds. And then when the N-channel FET is off and the current's passing through R2, it would have a pulse width of about 1 millisecond. So this would give us about a 180-degree turn. And here's some of the time domain plots from MATLAB of our keywords. As you can see, go starts out with kind of the glottal like G, and then ends with the O vowel, and then stop starts with the high frequency S, and then you can see the TOP, so the op. And what's kind of interesting is you can see from the word open, the same that same OP phenome that appears in both words. And and then for close is a lot of high frequency content with the CL and SE. And here's some of our MATLAB results. These are the filter outputs for the DC motor keywords. So for open, for the beginning of the word, we see kind of an increase of content as the frequency spectrum gets higher. And as for close, we see a lot of low frequency content in the beginning. Well, but the scale is actually really small, so actually most of the content appears towards the end of the word. And as for our servo motor keywords, go, you see that kind of high frequency G and then end with the lower frequency O. And as for stop, you see the high frequency S to begin with, and then some of the lower frequency for the OP. And overall, our system accuracy ranged from about 50% to about 77%. We did trials of 10, and we did this 3 times for each word and for each of us, me and Ishmael. And overall, my words seemed to mesh better with the board. I achieved a slightly higher accuracy rate for pretty much all of the words. And the highest accuracy was stop, which had a overall accuracy of 77%. And in one of the trials of 10, we actually achieved a 90% accuracy rate. And some of our lowest accuracies were with open. And I'm not really sure why. Maybe just the meshing of like the beginning of the word or not catching that final N consonant. And as far as system improvements, our system could definitely use a lot of improvements. Um, we could have faster processing because right now our processing really takes a long time and it's not really practical at this point. And we could do that by having a parallel structure of our filters. Or also we could use IIR filters so that we wouldn't need such a high order of filters. And also it would help to normalize the incoming signal just due to the variations of loudness, how close someone is to the mic or how they kind of inflect their voice really throws a lot of variation into our current system. And also the comparison function that we have right now is really lacking. It it's really, vector to vector, and we don't really have any quite pattern matching. So if anything's shifted as far as the vector, it could be matched up, but it very well could be the same word, but just shifted a few windows, a few segments off. And so we could definitely use a better comparison function and some kind of time warping for that in which different windows would be compared and find kind of the best match throughout the segment. And in conclusion, we achieved all of our goals. There's definitely some improvements to be made in order for our system to be practical, but speech recognition is a robust problem, and that a lot of times requires complex algorithms in order to yield accurate results. Thank you, and you can view the demonstration of our project in the next video.